Some of these additional notes are things that we've done already, and some will extend things a little bit further and just give us a few more examples with these ideas. Now, permutations, if we wanted to group this into a larger branch of mathematics, it falls under combinatorics, which is just a fancy word for counting, because all we're doing is seeing how we can count things faster. So one of the first things that we figured out was the fundamental counting principle. That was our spaces. We made a space for every decision and put in the number of choices to count how many ways things can be done. So here's a new car. The owner has choices of colors, transmissions, and interiors. So he has 3 decisions to make. He needs to make a decision on the color, a decision on the transmission, and a decision on the interior. So we draw a space for each of those decisions. And then how many choices does he have for each of those decisions? For the colors, 3. Transmissions, 2. Interiors, 2. 3 times 2 times 2 gives us 12 different ways that the car could be built. And we saw with our examples earlier, we could also represent this with a tree diagram. Each decision is a set of branches, so you could have 3 for the colors, black, silver, red, then 2 branches off of there for the transmission, then 2 branches off of each of those. So just to show the first, you could have automatic or manual, cloth or leather. And so this first branch would represent the sample space, black, automatic, and cloth, and so on. And you could then have a systematic way of listing them all. Now these questions are a little bit different than what we did in our examples. How many 3-digit numbers can be using the 7 digits? 1, where you're allowed to repeat the numbers, and 2, where you're not allowed to repeat the numbers. Well, if we're having a 3-digit number, it's still fundamental counting principle with both, but our choices are going to be different. If we are allowed to repeat, we would have 7 choices for the first one, 7 choices for the second one, and 7 choices for the third one. 7 times 7 times 7. 343 ways. But if you weren't allowed to repeat, you would still have 7 choices for the first space, but then how many choices would you have for your second number? 6, because one number's been used up. And then how many choices for the third number? 5. 7 times 6 times 5, 210 ways. Now in example 3 and 4, we're still going to, and I would like you, we're still going to use the numbers 1 to 7. How many 3-digit numbers are even, and you're not allowed to repeat the numbers? And this is our first example that's going to have a restriction. It's still a spaces fundamental counting principle question, but you have a restriction that the number has to be even. So the number 1 way that this is done wrong is not dealing with this restriction first. So whenever you have a restriction, this is important. You have to deal with that restriction first. So we have our 3 spaces. The restriction is on our last digit. It has to be even. And if we deal with the restriction first, how many choices would we have there? Well, our even numbers are 2, 4, and 6, right? So it would have to end with one of those numbers. We only have 3 choices to put there. How many choices now do we have for our first number? 6. There was 7 numbers, but you've used up one of them. Now there's only 6 numbers left. And if you're not allowed to repeat again, how many choices do you have for this space? 5. for 90 ways in total. Okay, and I'm going to put that one in my mailbox. Okay. Look what happens if we try to do it in order. And you will want to do it in order because you like to work from left to right. So you have spaces, and you say, well, I could put any number here. I have 7 choices. Then if I'm not allowed to repeat, I would have 6 left here. But now the problem is, with the restriction, how many choices do we have? Well, you may want to say 3, because there are 3 numbers that are even. But what happens if in the first 7 you started and you chose the 2? Well, then you'd only have 2 choices here. But if you didn't choose the 2, it might be a 3. You see the problem that we run into? We don't know, oh, it might be a 2. Oh, but what happens if I used a 2 and a 4? Then it might be a 1. I really don't know what number goes here. Well, if it's even, this is how many choices you have, not the number. Okay, that's a good point, because you get confused with that too, right? You start thinking, I have to put an even number. In your spaces is how many choices you have. So if you dealt with the first 2 spaces first and went 7 choices and 6 choices, then you can't answer the last space because you don't know. It could be a number of different cases. But when you have a restriction, and you deal with that restriction first, say, I'm going to put either a 2, a 4, or 6 in my last space. Then I would only have 6 choices left for my first space, and 5 choices for my second, for 90 different ways. So for example, 4, I want you to try this one. Again, we're only going to use the numbers 1 to 7. How many are odd? And I want you to come up with 2 different ways to get the solution. Method 1. How many people did the same strategy, said this one is odd now? We have 4 choices, because it could be 1, 3, 5, or 7. We deal with the restriction first. Now you've used up one of your numbers for the first digit. There's no restriction anymore, but you would have 6 choices left. Now you've used up 2 numbers, you would have 5 choices left for 120 ways. Another strategy that we're going to be using, I call it the not strategy, because you count what you don't want instead of what you want. You count all the bad cases and subtract them from all the cases. Does that make sense? If you have all, which we calculated earlier, 210, and you subtract the bad ones, in this case, well, that's bab. And you subtract the bad ones, which in this case would be the even numbers. How many even numbers did we count? In the example before, 90. You get 120. Does that make sense? If you subtract all the bad ones, you're left with all the good ones in the end? So if you know the opposite of what you're counting, you could take that away from all of them. In this example, the regular strategy is fast. But in some examples, it'll be much faster to count the bad ones and subtract them from all of the cases, as opposed to just counting them directly. And we're going to see that later on. So this will be another important strategy that you have. And what's happening in this unit is that we're developing strategies. Every word problem that you read needs a strategy to solve it. So far we've had the spaces. Now we've had spaces with restrictions, so that's an added strategy to the spaces. We've had identical objects, and I've introduced you to the not strategy. Some questions will have a combination of a bunch of these. And so you have to use multiple strategies in the same question. How many 3-digit numbers can be created using the numbers 0 through 9 without repetition? Well, it's a 3-digit number. Now we have to talk about, well, we'll talk about what a number is in a second. Do we have any restrictions on this one? Yes? No? How many choices do we have for our first number then? 10? Okay, so I have a question. Is 23 a 3-digit number? Is that a 3-digit number? Or is that 23? All right. If it was a 3-digit code, you could type 023. But I think as a 3-digit number, we do have a restriction here. Our first number is not 0. So when we talk about our choices, we can put 1 through 9 in there, but nothing else. Does that make sense? Now, how many choices do you have for the second number? 9. Why is it 9 again? Because the 0 gets put back in, but one of the numbers is gone. And now 2 numbers are gone. We have 8. Multiply this out. 648 ways are possible. All right, so that is dealing with restrictions. Some other stuff, this is review. You've seen factorial notation. You get mental math questions like this to evaluate. When evaluating your mental math questions with factorials, you can simplify factorials when they're dividing, and you can simplify them by expanding the bigger one. In 7 and 5, obviously 7 is bigger, so we go, the definition says go all the way down to 1, but we can stop at 5 because there's a 5 factorial on the bottom. They'll simplify. You just get 7 times 6, which is 42. In the second one, the biggest factorial is 10. So I could start expanding 10 times 9 times 8 times 7 times, and I'm going to stop at 6 because I have a 6 factorial on the bottom and a 4 factorial. So these 6 factorials would cancel out. And now I have 10 times 9 times 8 times 7 divided by 4 factorial, which is 4 times 3 times 2 times 1. Can you see that the 8 would cancel it with the 4 and the 2? That would simplify. And 9 divided by 3 would just leave me with 3. So what am I left with? On the bottom, everything's simplified, so there would be a 1 on the bottom. In my numerator, I have a 10, a 3, and a 7. 10 times 3 times 7, 210. And then when we get to algebraic expressions with factorials, we still use the same idea of expanding the bigger one. So the first question you have to ask yourself, which is bigger, n or n plus 2? N plus 2 is bigger. And so we start expanding the top, n plus 2. 1 less than n plus 2 would be n plus 1. 1 less than n plus 1 would be n. That's where I'm going to stop because I have an n factorial on the bottom, and those would simplify. And so it simplifies just to n plus 2 times n plus 1. Now, all of these topics of counting where order matters is something called a permutation. And permutations can all be solved with spaces and choices. So for example, consider the letters A, B, C. If we wanted to write out all the permutations, I could do the spaces first to say, I have 3 choices for my first letter, then 2, then 1, which is 3 factorial, which is equal to 6. I know that there's going to be 6 ways I can rearrange the letters A, B, and C. And I can just sort of, the one starting with A, the one starting with B, and the one starting with C. And I can then write them all out and know that I've counted them all because there should be 6 in total. We've had our formula for permutations. This formula is on your formula sheet. But this formula we don't use very much because the R can be translated into the number of spaces you need, and the N is the number you start with. So we very rarely use this formula. Sometimes there's an algebraic question that gets you to use it, but for the most part, we just use our spaces. But if you think about some things like NPN, there would be n spaces starting with n going all the way down. Should make sense that that would be n factorial. But if you plug it into the formula, remember we had this definition before that 0 factorial was equal to 1? It's because of this formula that that definition needed to be. So if you had 3p3, that's like 3 spaces starting with a 3, 3, 2, 1. It would equal 3 factorial. But according to the formula, you would have 3 factorial over 3 minus 3 factorial, which is 3 factorial over 0 factorial. And this is the reason why 0 factorial is equal to 1, so that it works in situations like this. So when you get a permutation question, you could give your answer in permutation form, but most of the time, if you were asked to solve this, you'd use spaces. So the wind ensemble has 10 pieces of music. They're wanting to make a program with 4 pieces of music, and the order matters: what they play first, what they play second, what they play third, and fourth. So you have 4 decisions to make. 10 choices, then 9, then 8, then 7. If this was a multiple choice question, sometimes they list 10p4 as the answer in a multiple choice question to see, do you know the connection between the spaces and permutations? To other permutation questions, number of permutations of the word math. Notice all the letters are different. So it's just 4 factorial. Now some of the strange kind of questions that end up with permutations are ones like this. 5 people come in for math help and there are 12 desks. And because you put numbers into spaces, and because you put students into desks, the main mistake that happens here is someone draws 12 spaces to represent 12 desks. Well, we have to remember that in the fundamental counting principle, the spaces represent decisions. And you have to think, well, how many decisions are being made? not how many desks are there. The desks aren't making decisions. Student 1 comes in. They have to figure out where they're going to sit. How many choices do they have? 12 choices, right? Because there was 12 desks. Student 2 comes in. They look. Student 1's already seated. They have a decision to make, right? How many choices do they have? 11. We don't want to put 12 there. It's very awkward if you come into math help and decide to sit on somebody else's lap when they're already asking math questions. Okay? Third person, fourth person, fifth person, then 10 choices, then 9, then 8. This is the same as 12p5. Right? And the order matters because if you're sitting near my desk, you get better math help than if you decide to sit in the back corner. How many different seating plans could we have in this class? Now, if everybody's here, we are 24 people. And we have 5, 10, 15, 20, 25, 30, 33 desks. So we could go 33 P24. 24 decisions, because each of you would need to make a decision where you start. And if we go to our calculator and actually figure this out as a value, (33) math over to probability, number 2, 24. 33p24, we get 2.39, and then that E31 means scientific notation times 10 to the 31. So if we write out this number, 2392, 889, 555, and then I don't know the rest of the numbers, but it was e to the 31. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Whew. There. That would be how many seating plans are possible. Even if we just stuck to the desks that you're in and don't worry about the regular desks, does it make sense that it would be 24p24 or 24 factorial different seating plans? And sometimes I've had a competition and say I'll hit random on the seating plan just so that I can see. And if anybody guesses it completely right, the whole class gets 100% in the course, and you don't have to come till the end of the year. Right? But your chances, like, of guessing it right, there is a chance, though. There is a possibility. You want to try? I don't want to be the one to guess. Well, everybody gets a chance, right? Oh, and then the 1 year. So I shouldn't have done this, but it was kind of. I had one student. And they guessed wrong right away, but I said yes. And then I made them, and they're like so close. Had them going all the way to the end. And I'm like, no, just kidding. You're off. So, yeah. No, we're not, well, we don't, I don't think we have time right now. But you wouldn't get it anyways. You want to just see if you can get the first person? If I random, okay. Quickly with this section, I would like you to change this to identical objects so it matches what we had in our textbook. And so if there's letters in a word that repeat and you're trying to count the permutations, well, normally for egg, if there were 3 different letters, it would be 3 factorial, but because of the identical objects, you divide by 2 factorial. And in B, if you did Assissippi or Mississippi or something like that, count all the letters, 1, 2, 3, 4, 5, 6, 7, 8, 9. But we have 3 S's, 3 factorial, 2 P's, we'd have to divide by 2 factorial, 2 I's, divide by 2 factorial. We only have 1 E. If you wanted to, you could divide by 1 factorial, but 1 factorial is just equal to 1, so it's not necessary to put in there. So it's another strategy, and you have to be able to interpret a question and say, is this a question with identical objects? If it is, how could I change it into a word with letters that repeat in order to solve it? So this is like example 2 here. Contractor sold model homes of type A, B, and C, 3 of model A, 4 of model B, and 2 of model C. So here, do we recognize that it has identical objects in the question? Yes. If it does, can I represent it as a word? 3 of model A, 4 of model B, and 2 of model C. If all the houses were different, it would have been 9 factorial ways to arrange them on the street. But since we have identical objects, we need to divide by 3 factorial, 4 factorial, and 2 factorial. We're going to make this one interesting. First of all, John lives 3 blocks north and 6 blocks east of school. So this is his house. It's north. No, his house is over here. Whoops. There we go. There's the house. Here's the school.
Sorry for the interruption. The U of M presentation is moved to Alt Ed in A3. The U of M presentation is moved to Alt Ed in A3.
His house is 3 blocks north and 6 blocks east of school. And he's walking home. How many ways can this be done? Well, this is identical objects because he needs to go north 3 times and east 6 times. So it'd be 9 factorial over 6 factorial, 3 factorial. Now something happens, and this is where Sally lives. And all of a sudden, every time John walks home from school, he has to walk past Sally's house. He's a stalker. Maybe he's walking her home. Maybe they're dating, but maybe he's a stalker. We don't know. Okay? He has to walk by Sally's house. So now how many ways can this be done? And this might be a place where we count it by using the numbers. So first of all, there would be one way that he could go there, 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 or there. Right? 2 ways that he could go there. 3 paths to here. 3 paths to here. Can you see that he'll never go to these spots? Because they're not on the way home, and that would, if he went to those, then he would have to backtrack to get to Sally's spot. 1 plus 3, this will be 4. 3 plus 4, this will be 6. 6 plus 4, there will be 10 ways that he would get to Sally's house. And then, to get home, what's 10 plus x? Still 10. 10 plus x, still 10. 10 plus x, still 10. 10 plus, well, those x's are really zeros, right? And then this spot, 10 plus 10 would be 20, 30. Now there's 40 ways that he can get home. And then we could add a part C where there's a restraining order. He can't be within 3 blocks or something. How many ways can he go home?